We were discussing the nuclear scattering, and last discussion we had discussed the basics of what is called the scattering cross section. Say for example, if we are considering scattering of a light nucleus A, say alpha particle, with a heavy nucleus that is denoted by x, and producing another heavy nucleus, in general something else like y, plus some light particle B. So, this could be an alpha particle bombarding on some gold nucleus or some other nucleus, producing say, or scattering just produce and the resultant B and y can be in general different from x and A, but in particular cases like elastic scattering, it could be the same as well. We can also consider neutrons interacting with the nuclei and then producing some final states, either one neutron itself or something else, and accordingly either the same nucleus or a different nucleus different from x. So, in such cases we said we can define what is called the differential cross section d sigma over d omega equal to r theta phi over f n. We had defined this in the last discussion. So, please refer to that again. Basically, this r theta phi here is the rate of particles projectile or the particle of type B reaching the or produced or coming out at polar angle theta and azimuthal angle phi, okay, and d omega is the solid angle of the detector, okay, if and f is the flux of the incident beam, n is the number density of the target x nucleus, right. So, d sigma actually is then the probability to find B in a solid angle d omega around theta phi direction. Okay. So, this is what the physical interpretation of this differential cross section is. Now, as we said, we can put the detector at angle theta and phi to see or measure the rate of the B coming out at certain angles or certain positions. If our detector can also detect what is the energy of this B particle which are coming out, and we will see later that our detectors, particle detectors are capable of doing that. They are capable of counting the number of particles, they are capable of finding the energy of the particle and the momentum of the particle, including the direction. Okay. We can get all this information from the scattering experiment. So, suppose we consider such a case, and in that case define d sigma as the probability to find a B particle of energy between E and E plus d. Experimentally, we cannot actually determine the energy precisely, right. There is always an experimental uncertainty. And let us also consider the angular dimensions along with this. So, probability to find B of energy between E and E plus D, some small interval of energy, and in solid angle exactly the same thing as before. In solid angle d omega, okay, between or around theta phi. The solid angle around theta phi is sin theta d theta d phi, or okay. This then can be written as r theta phi. Now, the rate we are actually counting only the particles of type B, the particles B coming out with energy E, right, E divided by F n, that remains the same, the target, the influx of the flux of the beam and the target density, number density remains the same, and then you have to multiply it by d omega and d E. Now, if you consider r theta phi E over d omega, not over d omega, over f n d omega, okay, and let us integrate that over d omega, okay, or I will put this integration here. But consider B particle coming with energy around E in an interval d E. Okay. So, this will give you the number of particles type B coming out with energy around E anywhere around the nuclear, the potential scattering center, scattering nucleus. Okay. So, we have to integrate over the angle then. So, you can actually define d sigma over d E. Experimentally, you can measure this as we explained, and we can have also the double distribution d d omega. Okay. So, the above discussions, it will be, all these are experimentally we can obtain all these things. So, or d sigma over d omega, etcetera. Okay. So, these are very useful quantities. I mean, all of these will give you some information about the scattering potential. Okay. So, that is what the purpose of the scattering experiment. It is to find out what is the dynamics under the interaction of these nuclei, the projectile and the target nucleus. So, now we will not go into the details of the discussions or the detailed calculations, but let me just mention some qualitative features of Rutherford scattering. Rutherford scattering, as you know, is an alpha particle on some target nucleus gives you same thing. Okay. So, this is actually an elastic kind of scattering. So, you do not have different type of particles produced. The initial particle is alpha, the projectile is alpha, target is x, say gold or whatever, and then finally again there is no change in the things, it is just a kind of a Coulomb scattering. So, it is basically a Coulomb scattering. There is no change in the nucleus or any such thing. So, this is one type of reaction that you can think of. What happens is that you send alpha particles to the target nucleus. So, if you send it head on, if it is actually going to be exactly along the direction of along the line joining the alpha particle and the nucleus, target nucleus, then this alpha particle will go and then come back in the same direction. Okay. They will go and come back. Right. So, in such case, what will happen? What is happening? You have initially some kinetic energy, say E 0, total energy initially, or EI, let me call it, and then you have a EF. EF, let me find out the EF, or it is actually going and then returning from the sea. As it goes towards, reaches the nucleus, it feels the nuclear potential, and alpha particle, these are, if you are looking at the Coulomb interaction, both of these are positively charged particles, and the projectile will feel a repulsive force of the nucleus, and then eventually the potential will be strong enough to actually stop this and then push it back. So, that pushing it back will actually give it kinetic energy, and then it will be pushed back to this field. So, that is what one can think of. So, it is actually in the case of head on collisions, there is a point at which the velocity is 0, point of return or point of closest approach, so or R minimum. Okay. So, this is your nucleus and this is your alpha particle. So, let us say initial velocity is equal to V 0, kinetic energy, initial kinetic energy is equal to half m V 0 square, where m is the mass of the projectile. Initial potential energy, let us say it is far away from the target nucleus to start with. So, it is equal to 0, and total energy. So, that will give you the total initial energy E I to be equal to half m V 0 square, only the kinetic energy. Now, at the point of return, as I said, okay, at R minimum, where it actually starts tracing the position, the path back. Okay. Some kind of a semi classical thought this one is, but it is okay. We can get a qualitative picture of this by this reaction, kind of analysis. So, at this point, velocity is equal to 0, that will give you kinetic energy equal to 0, potential energy is basically Coulombic potential energy 4 pi epsilon 0. Let us, it could be in particular an alpha particle, but let us take as kind of an light nucleus with z number of protons in it. Okay, let small z number, small z, let me denote the proton number. For alpha particles, small z is equal to 4, and let us say the target nucleus has capital Z number of protons in it, right, and then in that case the potential is 1 over 4 pi epsilon 0 small z capital Z E square over whatever is the position, and in this particular case of the point of return, it is R minimum. So, this is the final energy. So, that is also the total energy, right. So, there is no kinetic energy, total energy is equal to this. So, energy conservation will tell you that initial energy half m V 0 square is equal to 1 over 4 pi epsilon 0 z z E square over R min. Okay. So, that is one relation you can keep in mind, or R min you can find from this what is the closest approach, etc. Okay. If it is not head on, if not head on, which means impact parameter B is not equal to 0. We did say what is impact parameter yesterday. Impact parameter is basically the distance between the direction of momentum and the direction of the head on collision system of the particle. In that case, it will scatter at say some angle theta depending on what your B is and what the Z or what the potential that this particle will experience. Now, we can make do a computation based on the quantum mechanical based on quantum mechanics and the perturbation theory of quantum mechanics, and we will get d sigma over d omega to be equal to z z e square over 4 pi epsilon 0 whole square 1 over 2 m v 0 square whole square 1 over sin square theta by 2. This theta dependence and on the cross section is an obvious thing now, right, since the way we have been discussing. Now, the angle at which the particle will come out will certainly depend on what is the impact parameter. Okay. Now, this also says, this expression also says that there is no phi dependence, which is again somewhat expected. It is expected because we have we are talking about a spherically symmetric potential. So, the only direction that we have here is this direction of this particle that is going towards this one, and beam is expected to be cylindrically symmetric. So, the cylindrical symmetry will tell you that there is no azimuthal dependence in this. Okay. So, as long as you have the beam, a uniform beam, okay, with cylindrical symmetry, then we do not expect any azimuthal dependence in d sigma over d omega. The other thing, okay, so the expression that I wrote was wrong, it is actually sin power 4 theta by 2. So, this particular dependence like 1 over sin power 4 theta by 2 is something which you can check what is the angular dependence of this d sigma over d omega can be checked experimentally. 1 over sin power 4 theta by 2 dependence is experimentally confirmed in Rutherford scattering experiments. Okay. All right. So, we will not go into any further details of this Rutherford scattering. We will discuss some other aspects of the scattering cross section etc., and some more detailed calculation of this when we actually come to the particle physics scattering experiments, okay, elementary particle experiments. At the moment, let us go back to the nuclear reactions and then say what kind of reactions are possible, etc. So, one is this type, let me call loosely type of nuclear reactions. One is A plus x goes to A plus x, which is actually a elastic scattering. Then you can have, so this is elastic Rutherford type of scattering, probably mostly with Coulomb potential interaction. Then if you have enough energy for the projectile, what can happen is this projectile can actually go beyond the Coulomb barrier. It has enough kinetic energy to actually go and then in fact interact directly enter the nuclear dimensions, go close enough to the nucleons, and then they can actually have strong interactions as well there. Okay. Nuclear force can come into picture or will come into picture at that time. So, Coulomb interactions or elastic Coulomb scattering like the Rutherford scattering will happen when the projectile has smaller kinetic energy, smaller in the sense that it is not large enough to go beyond or overcome the Coulomb barrier or Coulombic repulsion, okay. And then it will go and then the reaction will be something similar to what we just now discussed. But if the kinetic energy is much larger than that, then we can think about a situation where A plus X goes and interacts with the nucleons, resulting in some kind of production or realization of some kind of a compound nuclear state, which is not a stable one to actually stay there for a long time. Okay. So, let us say take a neutron, a high energy neutron or large enough energy for the neutron to actually penetrate, go near the nucleons. In that case, this neutron can directly interact with the nucleons through strong nuclear forces, and that will actually result in some kind of a compound nucleus is formed. And then this compound nucleus is not a stable nucleus, and it can actually therefore decay down to something else, say y plus b. And in one particular case, it may be that y is equal to x and b is equal to a with same or different kinetic energies compared to a. X could, y could be an excited state of x to start with, all those possibilities are there, or it could be a different nucleus. So, such possibilities are generally called a compound nucleus reaction. Typically, if you look at the cross section, okay, cross section sigma, and plot this against the kinetic energy of particle A. So, energy or total energy or kinetic energy of particle, the projectile A. Then, if you are expecting say some kind of a particular excited state of some intermediate nucleus, say, in that case the cross section will have some kind of large value around the energy, okay, of E star or around the for some values of E A, that will give in combination with the energy and the mass energy of the X, whatever is the excited energy of C. Okay. So, there will be some kind of a large cross section, and then when it deviates from that or becomes the energy of E A is larger than this from the value around which the cross section peaks, again it will decrease, the cross section will decrease, because that energy is now not the one which matches with the energy of the excited state. Okay. So, this kind of picture, like there is actually kind of a large peak observed in the case of, is an indication of compound nucleus formation in these reactions. Another possibility is that the nucleus that you are sending to the light nucleus, the projectile that you are sending to the target, interacts not with the entire nucleus, but with some nucleons at the periphery or at the surface. Such reactions are called direct reactions. So, in direct reaction, what happens is that the nucleons that you are sending, the light nucleus that you are sending, a neutron or alpha particle, goes beyond the potential Coulombic potential barrier and interacts with the nucleus, but it does not interact with the entire nucleus, or the entire nucleus is not really taking part in that reaction, or most in the case of compound nucleus formation. It's most of the nuclei are in kind of formation, take part in this thing. There is an exchange of energy, etc. The projectile spends enough time with this, etc. But here in the case of direct reactions, they can come interact with the nucleons at the periphery, the neutrons or protons at the surface, and then just go away, kind of this thing. Okay. So, such reactions are called direct reactions, where the only nucleons at the surface of target nucleus take part in the interaction. So, this is another possibility. In some cases, it is possible that we have some intermediate state between these two, that is also possible. And in fact, in some reactions it is possible that you have kind of direct reactions as well as the compound kind of interactions, etc. Typically, the way we can look at the direct reaction and the compound nuclear formation is that for the compound nuclear formation, the projectile will spend some time with the target nucleus, and therefore, the reaction time is typically much larger compared to the direct reaction, where it actually comes and then interacts quickly with the neutrons or protons at the periphery at the surface and then goes away. So, such reactions will are quicker compared to the other reactions, the compound reactions, etc. Then we can think about heavy nuclear collisions, okay, nuclear heavy nuclear interactions. Here you can actually think about two nucleons of similar type of same kind of energies. So, instead of a light projectile bombarding a heavy target, we can think about two nuclei of similar atomic mass, okay, coming together or heading onto each other, colliding with each other and producing nuclei. Okay. So, it is possible that they will come together, fuse together. Okay. So, they will fuse together and then again they will split into two or more, normally two has a large number of large cross section compared to more than 2. So, this will then be slightly different from the kind of reaction that we have, or the compound nuclear formation or direct nuclear reaction that we just discussed. In fact, the heavy ion collisions, heavy nuclear collisions are very important, and then they have a large significance to understand the dynamics of elementary particles even beyond the nucleons. Actually, you can think about very high energy reactions where the energies are so much that when they smash into each other, even the protons and neutrons are smashed into each other, so that they can go through the or go to the inside of the protons and neutrons and interact directly with the constituents of the protons and neutrons. We will come to this later, what are the constituents of neutrons and protons, etc. But such possibilities are there, and in such cases we will also get kind of a soup or a plasma state if our understanding of the reactions, nuclear reactions is right. So, there are experiments which are done at very high energies, where heavy ions with high energy heavy ions are collided on each other, and then you can observe various possibilities there, and then what what are the resulting finite states, and then what are the signatures of this, or what are the observations. Based on these observations, we can actually try to understand what are the possibilities with the dynamics of the nuclear reactions there. And then we also have nuclear fusion. You can have two light nuclei coming together and fusing to each other. Okay, fusion reaction, in which two light nuclei, say x 1 plus x 2 goes to some heavy nucleus x, okay, fused together to form it. The resultant nucleus may be unstable, or it could be, usually it is unstable, which will go down to something else. Okay. But and then you can also have fission reactions. Fission reaction can also be like you have a nucleus, a heavy nucleus, which disintegrates into two nucleons or three nuclei with somewhat the similar mass. Now, this could also be, it could be natural, or it could also be induced by actually sending some high energy neutrons or protons, usually neutrons. So, these neutrons will go and then disturb this heavy nucleus, and disturb this, so that it will actually disintegrate into some two light nuclei. So, such fission reactions are also possible. So, these fission and fusion reactions are useful in the sense that we can extract energy from such reactions. We will stop here and then continue with our discussion later.